So let us continue talking about vectors. So far, we learned that you can take two vectors and create a new vector by adding and subtracting those vectors. We also learned about scalar multiplication of a vector. Let U be a vector with components x1, y1, z1, and the second vector v with components x2, y2, and z2. You can take these two vectors and create a new mathematical object, a new vector with components. We add the components x1, x2. We create the first new component of this new object. We add the second components. And finally, we add the third components to create this new vector. Well, remember that to subtract these two vectors, it's nothing but adding u and the opposite direction of vector v. So it's going to be u plus minus 1 times vector v, which we define it this way: x1 minus x2, y1 minus y2, and finally the last component, which is z1 minus z2. For the scalar multiplication, scalar, a number, a fixed number, let R be a scalar, a number. It can be positive, negative, it can be a fraction, it can be radical, it can be 0, 1, negative 1, any scalar, any number works here. Then R times U, scalar multiplication, is equal to, remember that officially we say we distribute R into the components of vector U. So we have R, x1, y1, z1, which is equal to R times x1, R times y1, and R times z1. R can be any number. Well, let's talk about multiplication or product between two vectors. So this is our goal today, to talk about different types of products between two or more vectors. This is our goal. Product between vectors. When we're talking about products between vectors, we're dealing with two types of products. The very first one is called the dot product, inner product, and the second one is called the outer product or the cross product. We have two types of product between two. Eventually, remember that when we are talking about two vectors, we can generalize the idea to more vectors. The very first one is called the dot product or inner product, and the second one is called the cross product. So we're going to write these two side by side and compare these two operations between vectors. So let us start by talking about the dot product between two vectors. So let us have two vectors. Let U be vector x1, y1, z1, and V be vector x2, y2, and z2. The dot product between these two vectors is denoted by U dot V. We put a dot and we call it dot product or inner product. How do we define this product? Well, we take the corresponding components of these two vectors, multiply them together, and finally add those multiplications. So it is x1 times x2 plus y1 plus y1 times y2 plus z1 times z2. z1 times z2. So take a look at the dot product. Here you have multiplications of two numbers, and eventually you add all of these numbers together. So the dot product between two vectors is nothing but a number or a scalar. So let me write this down here as a note. It's important. The dot product is a number. It is just a scalar. The outcome is not a vector. Okay, let's talk about the cross product or outer product between two vectors. Let us work with the same vectors, vector u and vector v. When we define the cross product between two vectors, we are actually creating a new vector which is perpendicular, orthogonal to both vectors u and v. The cross product between two vectors is a new vector which is perpendicular or orthogonal to both vectors u and v. This is important for us. Why is that? Because in the next section, we're going to talk about planes. To form a plane, we need a normal vector to the plane, and we can use the cross product between two vectors to define that normal vector. Very well. So how do we define cross product between two vectors? Remember that when we learn about matrices and determinant, we define the determinant of a matrix this way. So this is a short recall. Let A be a matrix, A, B, C, D. The determinant of matrix A is defined as AD minus BC. It's a 2 by 2 matrix. If you have another matrix, 3 by 3, let B be a matrix, A, B, C, D, E, F, G, H, I. The way that they define the determinant of 3 by 3 matrix, like B, is this way. Here we have A times the determinant of this submatrix, EI minus FH minus B times the determinant of this small submatrix, DI minus FJ, and finally plus C times the determinant of this submatrix, which is DH minus EG. So we're going to use the determinant of the 3 by 3 matrix to define the cross product. So let me put this double arrows here for you. So you know that we're going to use the determinant of a 3 by 3 matrix to define the cross product. So the cross product of these two vectors is denoted by U cross V. put a cross between these two vectors? Well, it's equal to the determinant of this matrix. Well, on the very first row, we're going to use standard vectors I, J, and K. This is always fixed. On the first row, we're going to use the standard basis vectors. On the second row, we're going to write down the components of the very first vector, vector u. X1, Y1, Z1. And on the last row, we're going to copy down the components of the last vector, which is vector v. So here you have x2, y2, and the z2. Well, following the definition of a determinant of a 3 by 3 matrix, it is equal to, well, we have I, so I times the determinant of this small submatrix, which is equal to, here we have y1 z2 minus y2 z1 times I in the direction of x-axis. Remember that we have the subtraction, so we're going to put subtraction here, minus, well, here we have j times the determinant of this submatrix, so we're going to have x1 z2 minus x2 z1 times j in the direction of y-axis, and plus k times the determinant of this small submatrix, which is x1 y2 minus x2 y1, again in the direction of z-axis. So we're going to have k written down here. The cross product between two vectors is a new vector. The outcome is a new vector with the first component, second component, and the third component. The outcome is a new vector perpendicular to vector u and vector v. So if you have vector u and vector v, this is the cross product between these two vectors. So note that the cross product is a vector. Compare the dot product with the cross product. The dot product is just a number. The outcome is a number. We do just a simple algebra, and outcome is a scalar. It might be 0, it might be a negative number, positive number, it might be fraction, it might be radical. But the cross product between two vectors is definitely a vector. Very well, let's go over a couple of examples. I'm going to copy down the cross product formula up here for you. So when we follow the definitions, they have all of them written here. So when u is x1, y1, z1, and v is x2, y2, z2, and u dot v is x1, x2, plus y1, y2, plus z1, z2, the dot product, and the cross product, u cross v, which is the determinant of I, j, k, x1, y1, z1, x2, y2, z2. Very well. So In this example, question says, find the dot and cross product of the following vectors. Here we have -1, 7, 4. So vector u, -1, 7, and 4. And the second vector, vector v, is equal to 6 to -0.5. 6 to -0.5. Well, let us find the dot product first. Then we're going to check the cross product. So for the dot product, u dot v, it is straightforward. We multiply the first component, -6. We multiply the second component, 14. We multiply the third component, -2. Well, here we have 6 as the dot product between two vectors. For the cross product,